Welcome to a short video on three-dimensional surfaces in MATLAB and Octave. MATLAB and Octave are both mathematical software packages that can do various things. Octave is very close in its programming structure to MATLAB. So I would say probably 95% of the commands in Octave are identical to the commands in MATLAB. So what I'm about to show you should work in either of these software packages. What we're going to look at are meshgrid, mesh, and surf. Those three commands or functions in MATLAB. They have exactly the same spelling and use in Octave, I believe. I'm going to be using Octave to make this video. If you try it in MATLAB, I think it'll probably work there too. So first, let's ask, what does meshgrid do? Here is a program to plot z equals x squared minus y squared. And we're going to, over the next few slides, look at what this program does. So first, let's see what's happening here at the beginning. What's in green here is a comment. This is a program called meshIt, which produces two mesh plots for the same data, each arranged in a different order. I'm going to create two figures, figure 1 and figure 2. And we're first going to look at what happens with this part of the code here in creating a surface plotted using the mesh command. And the figure is going to be called figure 1. So let's see what happens here. We first define an array which we call xvalues, which just has the numbers 1, 2, 3, 4, 5, and 6 in it. We also create another array yvalues, which has 1, 2, 3, 4, 5, 6 in it. Then the next line, we're going to use the meshgrid command. The array which has x in it first, y in it second, two arrays, capital X, capital Y, is equal to meshgrid of the x values and the y values. The x values were 1 through 6 in order. The y values were also 1 through 6 in order. When line number 8 is executed, what are the values stored in x and y? If we look over here, here's part of the output. X is this two-dimensional array. But notice that x values was a one-dimensional array. Capital Y is also a two-dimensional array. And what do we notice about these? In X, the first column is 1, second column is 2, then 3, then 4, then 5, then 6. So it's stored in this array capital X, this array, and the column values were the same as the X values here. What about Y in this line? Capital X, capital Y equals meshgrid of X values, Y values. Stored in Y after this is executed is this two-dimensional array. The first row is 1, second row is 2, then 3, 4, 5, and 6. Then we execute z equals x squared minus y squared. The dot here means that we're performing this as an array operation on x. We're squaring every element in the array x that we have up here. We're also squaring each element in the array y down here, and then we're subtracting them. When you do that, when you look at x squared minus y squared, z is going to be this two-dimensional array. Where did this 0 come from? It's 1 squared minus 1 squared. So the 1, 1 entry of x was squared, the 1 of entry of the 1 entry of y was also squared. 1 squared minus 1 squared is 0. How about this minus 3 here? This is in what? The second row, first column. So if we go to the second row, first column of each of these, we'll be looking at 1 squared minus 2 squared. 1 minus 4 is minus 3. Let's just look at another one down here. How about this minus 7 that we have? And where is that? That's in the fourth row, third column, isn't it? So if we go to the fourth row of x, third column, we have a 3. So we're going to have 3 squared minus the y squared value, which is in the fourth row, column 3 again, and here we have a 4. 3 squared minus 4 squared is 9 minus 16, and that gives us the minus 7 here. So basically, what MATLAB is doing is, when it's computing values here, z is going to be a two-dimensional array, and we get it by looking at the two-dimensional array x squared minus the two-dimensional array y squared, and that gives us this two-dimensional array stored in z. The next thing that's executed is mesh x, y, and z. So what does that look like? This is the mesh stored in figure 1. We can rotate this a little bit if we want to see other views of it. Perhaps this is the easiest to see. On the y-axis here is 0, and we do have some places on this graph where the height is 0. But this is the correct graph of the function that we were looking at. So if we just look at this first part of the program that creates figure 1, we have seen that figure 1 looks like this. We have a smooth surface representing the equation z equals x squared minus y squared. If we used surf xyz instead of mesh xyz, we would get a graphic output that looks like this. The surface is colored, so it's easier to see what's the surface and what is not. But we can see that it also shows us those grid points that we had, which were used in the plot. Often this sort of thing, surf xyz, gives us something that we would appreciate a little bit more than the mesh diagram. So now let's look at the code that produces our second figure. We'll let uValues be the one-dimensional array containing 1, 6, 2, 5, 3, 4. We'll let vValues be the one-dimensional array also containing 1, 6, 2, 5, 3, 4. Then we'll execute this command. Capital U, capital V equals meshgrid of the uValues and vValues. So if we look over here, what was stored in U? We have a two-dimensional array here, and the columns are 1, 6, 2, 5, 3, 4. If we look at what happens to capital V, it's going to be this two-dimensional array where the rows are constantly 1, 6, 2, 5, 3, and 4. Then we're going to execute W equals U squared minus V squared, which is analogous to what we had up here, Z equals X squared minus Y squared. Only we're calling things U, V, and W instead of X, Y, and Z. And we just changed the order of those same numbers in these two arrays. And so W is going to have the same values as Z, but are they in the same places in that two-dimensional array? And what will that do to our graph when we look at mesh uVW? Well, first of all, let's look at this line W equals U squared minus V squared. W is this two-dimensional array. And let's just look at maybe a couple entries here. Where did this 0 come from? That was 1 squared minus 1 squared, U squared minus V squared. How about this entry right here, this 0, which is in the third row, third column? That 0 came from 2 square minus 2 square. It basically was using this 2 right here and this 2 right here to get 0 right here. So we can see that if U is 2 and V is 2, then W is 0. And that's the same calculation that would have been done in the first part, but now it's in a different place in that array, isn't it? So, can MATLAB or Octave sort this out and still give us that smooth curve that we saw before? Stay tuned and we'll see the answer of that almost immediately. And this is the figure 2 graph where we have the same x and y values, which were called u and v in this case, but they were in a different order. But u order and v's order were the same. So when we mesh the two together, we still get the corresponding w values the same as the corresponding z values. If we rotate this one around to see what's happening, we can see that things just did not work out at all as far as getting that surface. So what we got for the second output in figure 2 is not the same as the function that we were considering. So the MATLAB code, or equivalently Octave code, that produced figure 2 gave us what looked like overlapping shingles and not really the smooth curve that we would expect for W equaling U squared minus V squared, where we are graphing in the UVW plane. So I guess the moral of the story here is that we should keep these in ascending or descending order so that the meshgrid and mesh functions produce data that can be used to make our smooth graph of U squared minus V squared.